Let's talk about line integrals. Now there's two kinds of line integrals, so we will deal with the first kind today. Just to connect things up first though, let's do the following. Let's say that throughout the previous chapter, setting up an integral had two matters or ingredients, and these ingredients were completely independent of each other, to be really honest. I mean, they could be anyway. So we had one thing was the function. We had to talk about what function we were going to integrate. So the function, maybe it was f of x comma y, or in a three-dimensional setting, integrating the function f of x comma y comma z. Yeah, the function that you're integrating. And let's just put in this friendly reminder here that we had the case of the f of x comma y comma z is just the constant, always gives you the output 1 for computing volume, for instance. Yeah. The other key ingredient was we needed the region, which was often denoted like D or maybe E, whatever letter, it doesn't really matter. But there was a region of integration. We're going to integrate over. We've integrated over boxes, and we've integrated over filled in rectangles in 2D, or filled in ellipses in 2D, or we've integrated over like solid spheres in 3D and so on. Okay. Yeah, and just, even though I think I already said it, let's just mention, and the function, that's this part here, and the region, that's the second part here, are really independently determined. Independently determined or described or whatever, right? What I mean is, it's not like I would give you the function and then you would automatically know the region, or that I would give you the region and that you'd automatically know the function. That's not how it works. Like, it's not like one is built from the other. Both things need to be provided if you need to do an integral problem. What I mean is, if I left out one of the two pieces and asked you to do something on a quiz or exam, you would have to complain and say, you didn't give us enough information, right? So let's take a look for the function. Let's look at an example. F of x comma y equals x squared y. So there's the function part. And then maybe we're going to integrate over the following region. So integrating over, say, the filled in box. So 1 to 8 for x values times 2 to 6 for y values. Okay, so there's the two parts. There's a function part, there's the region. So they have to be both described, and neither has to relate to the other, right? So this was, like integral 2 to 6 of integral 1 to 8 of x squared y dx dy. Now, the new thing we're going to do is we're going to take this and say, instead of integrating over, well, that picture, let's draw it, right? So instead of integrating over, okay, x went from 1 to 8 and y went from 2 to 6, instead of integrating over this filled in region here, okay, this might have been called like capital D, right? Instead of this solid, filled rectangle, what if we integrate over the same function, f of x comma y equals x squared y, over not this filled in two-dimensional thing. In fact, not a two-dimensional creature at all. How about something that's, in terms of, in its nature, it's a one-dimensional creature that's described in two-dimensional space. So over what? How about over, well, how about this, just to make it as similar as possible to the last example. So not a filled in two-dimensional object, but a one-dimensional object living in two-dimensional space. So how about there, there, that, and we'll go travel this way. Okay, so this is a line segment. So here earlier we had a filled rectangle. This shape I'm trying to describe right now is just a line segment. Yeah, the line segment that connects the point 1, 2 to the point 8, comma 6. Okay, so I'd like to integrate, that's what we're building up to. I would like to talk about integrating a function with two input variables, like x squared y, but not over a filled in rectangle, just over line segment. Or over, okay, that would be nice. This is a nice shape, but how about even over a different shape? So how about like the following? So let's say, okay, 1, 8 still on the x-axis, y-axis still 2, 6. So we'll start at 1, 2 again, and we'll end at 8, 6 again. But what if we created some kind of integral that did this? And we're going to travel along this curve called C. Okay, so what we're trying to do is we're trying to expand a little bit where integration applies, and we want to talk about integrating this function no longer just over this, but over this curve. Okay, so this is what's going to be called a line integral. The name is a little unfortunate. Okay, we haven't set it up yet. It's going to come later. The reason I want to bring this up right now is this C here does not look like a line, right? This C is a curve. Okay, we will still use the phrase line integral. Maybe a more appropriate term would have been called curve integral. Probably better name. Maybe, question mark, but nobody calls it that. So we're just going to call it a line integral. Okay, we're just going to deal with it. This is just a very creative line in the fact that it's not a straight line like this is. Okay, now let's start easy and build up the ideas that we need. So the integral, let's start a new. I'm gonna stop this video, start a new one.